Right now, the world's most advanced artificial intelligence is running into a physical wall. It is not a lack of data, nor is it a shortage of electricity. It is a simple, brutal mathematical equation. If you double the size of an AI's input, the computing power required does not double. It quadruples. This hidden quadratic bottleneck is why the trillion-dollar AI industry is quietly searching for a replacement to its greatest invention. In 2017, the transformer architecture arrived and quickly established a total monopoly over artificial intelligence. Its core engine, called self-attention, allowed computers to process data in a way that felt almost human. Instead of analyzing text one word at a time, it looked at the entire sequence at once, establishing context and relationships between words instantly. This sequence-to-sequence approach quickly took over fields far beyond language. Computer scientists realized that if you could treat image patches as a sequence, you could use attention to analyze visuals. By 2021, researchers used this exact architecture to map the three-dimensional structures of proteins, unlocking secrets of biology that had stumped humans for generations. But as we began feeding entire books, code bases, and genomes into these models, we exposed the fatal flaw at the center of attention. To understand the crisis, we have to look at the math. When a transformer processes a prompt, every single word must compare itself to every other word in the sequence. If you type a 10-word sentence, the model performs 100 comparisons. If you feed it a 10,000-word document, it performs 100 million comparisons. This is quadratic scaling, written mathematically as O of n squared. As the context window grows, the memory required to store these comparison matrices explodes. It rapidly fills up the ultra-fast, ultra-expensive high-bandwidth memory of modern graphics chips. This is not just a software challenge. It is a hardware chokehold that makes long-context AI incredibly expensive to run and scale. Imagine you are a detective trying to solve a complex case using a massive stack of files. The transformer is a detective with perfect photographic memory, but who has a bizarre limitation. Every single time a new clue arrives, they must reread every single page of the case file from the very beginning to understand the context. They never forget a detail, but as the files stack up, their brain eventually melts from the sheer volume of reading. Now, imagine a different approach. This detective carries a pocket-sized notebook. Every time they read a page, they write down a brief, highly compressed summary of the essential facts and discard the raw paper. This notebook represents a state space. It is a mathematical description of the system's current status. The notebook is small, constant in size, and never grows, no matter how many pages are added. You might lose some microscopic details, but you can process a million files without your brain exploding. This notebook approach is the core of the state space model. While they sound like cutting-edge artificial intelligence, these models actually trace their lineage back to classical control theory used to guide Apollo spacecraft in the 1960s. Recently, researchers realized these equations could be adapted for modern deep learning. Instead of comparing every data point to every other data point, a state space model compresses the entire history of a sequence into a single, hidden mathematical state. As new data flows in, this state is updated continuously. Because the model only needs to update its current state rather than looking back at the entire history, its computational cost scales linearly. This is O of n. If you double the length of the input, the work required only doubles. For the first time, we have an architecture capable of processing millions of tokens of context on consumer-grade hardware. But if state space models are so efficient, why hasn't the industry thrown out the transformer entirely? This is where the standard narrative falls apart. There is a fundamental trade-off. Because state space models compress everything into a fixed-size state, they suffer from a form of memory loss. If you hide a specific, random sentence deep inside a massive, 1,000-page document and ask the model to retrieve it, it will often fail. The transformer, with its massive quadratic memory, can pinpoint it instantly because it retains the entire raw history. Furthermore, modern hardware is actively working against this new architecture. Graphics processing units are physically designed to perform massive, parallel matrix multiplications all at once, which fits the transformer perfectly. State space models require sequential updates, which run slowly on standard chips. We are trying to run the algorithms of tomorrow on hardware optimized for the algorithms of yesterday. To bypass these hardware and memory limitations, researchers designed a breakthrough architecture called Mamba. Mamba introduces a selection mechanism that allows the model to actively decide what to remember and what to discard, mimicking the precision of attention while keeping the efficiency of linear scaling. But the real shift is happening through hybridization. Instead of choosing between the two, engineers are now stacking transformer layers and state space layers together in a single system. This hybrid approach gives models the sharp, exact recall of attention for critical details, while using state space layers to handle the massive, continuous streams of background data. It is already showing remarkable promise in genomics, where models must analyze DNA sequences millions of base pairs long, and in clinical medicine, where an AI must process decades of a patient's medical history to detect hidden correlations. We are witnessing the end of the brute force era of artificial intelligence. The industry can no longer rely solely on buying more chips and consuming more electricity to power inefficient algorithms. As the economic reality of the quadratic bottleneck sets in, the architecture of intelligence itself must evolve. The shift toward state-space models is not just an academic exercise. It is a quiet, structural realignment of how computers process information. By breaking the O of n-squared limitation, we are moving away from models that merely respond to prompts and towards systems that can digest the continuous, infinite streams of the physical world. The reign of the transformer is not over, but the walls are closing in.